will show you how to saturate the double bond. We have alkene with a double bond that we're going to add a strong acid like HI, HBr, or HCl to it, and we'll turn it to single carbon-carbon bond. And also the halide will be added to one of the carbon. The question is where I should add the halide. Does it matter? And how to figure that carbon. Let's start with the simple case. Simple case, we have a double bond that double bond, if we look to it, that double bond, it has two hydrogen on each carbon, okay? And it has identical substituent. So the substituent are identical. In this case, both of them are ethyl. Okay, doesn't matter where to add like the bromide. In this case, no, it doesn't matter. The first step of this reaction is going to start with the nucleophile is going to attack the hydrogen. Hydrogen, it has a positive charge. How do I know it has a positive charge? Because it's attached to bromine, and bromine is more electronegative. And bromine will take these two electrons, and the alkene will go after hydrogen, and it will take the hydrogen. And the first thing that we're going to get, it will be this. So double bond, okay, is gone. We don't have double bond anymore. From now, okay, we have hydrogen added to one of the carbons. The second atom, now it will have a positive charge. So we got a carbocation. Remember, we do have hydrogen. Okay, so we do have hydrogen on each of this carbon. And we have those hydrogen from the beginning. So one of the carbon now is saturated, while the second, it has a positive charge. And this one, it will be the intermediate. Of course, you have a bromide somewhere there. Bromide, it has a 4 lone pairs. So bromide, it has negative charge. It will be -1. And then next step, this bromide will be added to the system. So bromide will be the nucleophile, and it will attack carbon with a positive charge. So I'm going to take this species and add the bromide to it. Okay, so next step, as I said, okay, bromide will be added to this carbon, and the final product will be this one. Okay, so now negative charge, the positive charge is gone. We don't have positive charge anymore, and bromide, it will be added there. Here you go. Now I got bromide. Okay, as you see, bromide can be added to any carbon. It doesn't matter any way. Okay, anywhere you add the bromide, the product, it will be this. It will be 1, 2, 3, 4, 5, 6. It will be 3 bromo hexane. Okay, so product will be the same. It's going to be 3 bromo hexane. Okay, now what will happen if it's not symmetrical? Okay, if the double bond is not symmetrical, for example, in this case, we have a double bond that one side of it, we have 2 carbon, another side, we have hydrogen attached to carbon. So we have hydrogen there, here you go, hydrogen there. Okay, that means this carbon, top carbon, and this one is attached 1, 2, 3. This one is tertiary carbon. Well, here, this one is a secondary carbon. Okay. Now, there are 2 possibilities. One possibility is, let's say, those 2 electrons of the double bond, they will go after hydrogen, and hydrogen will be added, okay, to the side. Okay, to a carbon, hydrogen will be added to a carbon that has more hydrogen. Listen carefully. Hydrogen, the H+, will be added to a carbon that has more hydrogen attached to it. What does it mean? It means the order for it is less. okay, you will add it to a carbon that has less order. Tertiary versus secondary, we're going to add it to the secondary. So here you go. This is the hydrogen that we added. Now, what do we get here? We get a positive charge. And now what should what's the order of this carbocation? This carbocation is tertiary. Okay, next step, you have the bromide, which is the nucleophile. This is equal to the nucleophile. Nucleophile, now it can attack this carbon, and nucleophile will be added there. So we get the bromide here. Now bromide attached to it. And of course, there I got two hydrogens. Okay, I had one hydrogen from the beginning, and that hydrogen, and I believe it's a green color. The green color is the one that came from HBr. Okay, and so that's one of the product. Okay, or let's go with this. Okay, we're gonna again we have a double bond. Okay, that double bond is gonna go after hydrogen. We'll take H plus from HBr, and this time we're gonna add the H to the tertiary carbon. Okay, to the tertiary carbon. Now that carbon is octet. So now we're gonna get a positive charge. And where is the positive charge? Here. This carbon is the secondary carbon. Okay, remember the top one was tertiary, now is the secondary. Next step, the bromide, okay, or the nucleophile will attack this carbon. And we're gonna get bromide here. And again, remember that we do have hydrogen from the beginning. There was hydrogen from the beginning there, and now this carbon is octet, and I got hydrogen here. Okay, let's highlight position of the bromide. Okay, bromide is there. Bromide is here. Okay, now what's the difference between them? The first one, bromide is attached to a tertiary carbon, and the second one is attached to secondary carbon. Okay, which one of this is going to be the major product? Okay, let's talk about the intermediate. We're gonna have activation energy. I want to talk about those two activation energy. Let's call this one. We call one print. The second one print. And the first one, if you add hydrogen, the acidic hydrogen that comes from the acid, if you add it to a carbon that has more hydrogen attached to it, you will get a carbocation that is a tertiary. Well, if you add it to a carbon that, if you add it to a carbon that has higher order, it's already tertiary, you will get a carbocation with lower order. Okay, I have a tertiary versus a secondary. Tertiary is more stable. So I'm going to say tertiary carbocation, okay, tertiary carbocation is more stable, okay, is more stable than a secondary carbocation, okay, because the intermediate will be more stable, okay, for the first reaction. Intermediate for the first reaction is more stable. I'm going to say the activation energy for first reaction is going to be less than activation energy of the second reaction. Okay, the second reaction, or let's call this one the second reaction. In that case, okay, that means the first reaction is going to be faster. So this reaction, it will be faster. Okay, this type of selection, we call it Markov-Nikov. Okay, the Markov-Nikov says add hydrogen, or add the acidic hydrogen to a carbon that has more hydrogen in order to get carbocation with higher order. So this product will be Markov, I think Markov-Nikov products. I think Markov. Let me double check that. It's a Russian name. Let me double check the pronunciation for it. And so it's Markov. Yes, the pronunciation is going to be Markov-Nikov's product. Markov-Nikov product, it says put the bromide on a carbon that has more substituent. Put the bromide or the halide on a carbon that has more substituent. That means generate a carbocation with more substituent. Okay. Now, whenever you add the H, okay, and you're gonna get a carbocation. Remember, we got the carbocation or we got the intermediate. This part we call it an intermediate. Okay, so that one I'm gonna call it intermediate. Okay, we said the tertiary intermediate is more stable than the secondary. So we added the hydrogen here, and we got the tertiary. We got a tertiary carbocation. That tertiary carbocation, it has an empty orbital. And this is the empty orbital. Okay. Now, we can, the nucleophile, it can reach it from the top or the bottom. Why? Because this carbon, okay, the carbon that I'm going to highlight, this carbon is completely, it has a trigonal planar geometry. That means it's going to be a flat. I can reach it from the top or the bottom. Okay. And so remember, in all this structure, we added the hydrogen here. So I'm going to put the hydrogen there. Okay. Now, if I add the nucleophile from the top, so from top, if I add it from the top, that means bromide, it will be here, correct? Okay. And if I add it from the down or bottom, then bromide is going to be there. Now, let's draw them. Now, we have a carbon here. This carbon is going to be tetrahedral. So that means bromide, it will be pointing up, while the methyl, it will be down. This is going to be CH3. This one is bromide. And, or you can, okay, if you add it from the bottom, bromide will be at the bottom. And so forgive me, bromide will be down. So bromide, my bad, it will be here. This is going to be a bromide, and methyl this time. Will be up. This is the methyl group, okay, or CH3. Okay, let's assign the configuration. Now we got the stereocenter, and we need to assign the stereocenter. So I got the stereocenter there. Okay, the first one, I have bromide. Okay, it's gonna get the highest priority. Next priority is gonna be this carbon. Okay, why that carbon? Because that carbon is going to be neighbor to this substituent. Well, this carbon is neighbor to CH2. Okay, CH2. Here we have CH, CH3. Okay, so this group is going to be heavier technically than this one. And if that one is number 2, number 3 is going to be here. And what's number 4? Number 4, it will be the methyl. And where is methyl? Back of the molecule. Now let's assign the configuration. The configuration in this case, if we follow the numbers, it will be counterclockwise, and this is going to be S configuration. So if we add bromide from the top, we get S configuration. But if we add the bromide from the bottom, we get bromide 1. This is going to be 2. This one, it will be 3. Okay, the order this time, okay, the order here, okay, is going to be counterclockwise, but you need to ask yourself, where's the heaviest, like where is the lowest priority? The lowest priority, which is methyl, is pointing to us. Okay, methyl is pointing to us. Because methyl is pointing to us, we need to flip the configuration. right now I see it S, so I'm gonna flip it to R. Okay. The bottom line, or the thing that I want to say, whenever you're adding H, okay, HBr to an alkene that it has different groups, there is a chance that you might get a stereocenter. Okay, and if you get a stereocenter, you have two possibilities. You might add actually the nucleophile from the top or from the bottom, and that's gonna give you SNR or RNS. In this case, I'm gonna say you will get 50% from each enantiomer. So 50% from each enantiomer. Okay, we get equal amount from both of them. Be careful about this one. And so we're not gonna get optical activity. So no optical activity because they are 50-50. Okay, and one more thing that I want to say. Okay, let's go back for a second here. What's the meaning of reduced selectivity? Reduced selectivity. Okay, it says the hydrohalogenation reactions are reduced selective. What does it mean? It means the reaction is favoring one of the carbons. Okay, and instead of adding the bromide to a secondary carbon, is adding it to tertiary carbon. Okay, if your reaction is favoring one region, listen carefully. If the reaction is favoring one region, we say the reaction is reduced selective. A reaction is, instead of this region, is favoring that region, favoring the tertiary carbon. So I'm going to call it reduced selective. Okay, and that's the meaning of the reduced selectivity. And last thing that I want to talk about it, we have such a molecule, and we're going to add H to it. And if I add H, this one it can happen. So let's add the H here. That means we're going to have a positive charge here. Next step, the chloride will attack it, and we get this product. So chloride will be added here, and hydrogen was added there. Okay, that's one. Okay, what did I get here? I got secondary carbocation, and then nucleophile attacked it. Our nucleophile is the chloride, and the chloride went after this carbon and made it saturated. Okay, or okay, again, we're gonna add hydrogen, okay, to the side that it has or to the carbon that it has more hydrogen, and this one it has two hydrogen. Well, here we have only one carbon, so we're going to attack the terminal carbon. Okay, now we have three hydrogens there. Okay, this is the hydrogen that we added, and of course we had hydrogen before. We had two of them. Okay, what else? I got a carbocation here. Now this carbocation is a secondary carbocation. Okay, is it possible is there any chance to turn it to a tertiary? Okay, by moving just one sigma. Okay, let's zoom on this carbon. Okay, on this carbon, what do we have? We have two methyl groups, and the third substituent will be hydrogen. There is a hydrogen here. Okay, if you move this hydride, if you move it, if you do 1 and 2 hydride shift, so 1 and 2 hydride shift, you will get this carbocation. And now we will have a tertiary, okay, tertiary carbon. Okay, and this tertiary carbon, it will be attacked by chloride, and because it's more stable than secondary, your final product will be this. So chloride, it will be added here. Okay, so as you see, instead of adding the chloride to the second carbon, the chloride now added to, if we start from the left, it will be the third carbon. Okay, and so if there is a chance to do rearrangement and get more stable carbocation, then do it. Okay, and thank you very much.